set structure, so there is no question of movement of dislocations. Uh, so the mechanisms for polymers are, if we have linear polymer, then simply we increase the length of the polymers. That the increases the strength. But I also pointed out last time that sometimes in many, or not sometimes, but in, I would say, in many situations where strength is not a big issue, in those cases we add some weaker material or weaker short chain polymers which provide lubrication to the flow of polymer, and that increases the production rate. So one of the biggest reasons or one of the biggest advantages of using polymers is that we can produce materials at a very low cost. And low cost means, of course, the production rate, the faster the production rate, the lower will be the cost. So if strength is not an issue, we want to produce as much material as possible, as quickly possible. So in such situation, we add some lubrication, we add some polymer which increase its lubricity, and that increases the production. But for branch polymers, yes, if we, because the branches they get entangled in each other, and once we have like the greater the number of branches, the greater will be the entanglement, and hence there will be more. Then strength will be increased. So degree of branching is indicative of the strength of polymer. The higher the degree of branching, the stronger will be the polymers. Uh, then we have again. I will reiterate. Uh, if you have any questions, please unmute yourself or stop me and ask. I see that there's a number of queries, but those are about quizzes. So if you have any question on the course, please unmute yourself and let me know. Uh, So I was talking about cross-linking. Uh, when we have polymer chain, and if we lightly cause some cross or small amount of cross links between some chains, then cross-link would mean adding primary bonds between adjacent chains. Uh, so that would basically uh, we know that normally for other branch or for linear polymer, the chains are not connected to each other. But adding cross links would connect chains by primary bonds. So it makes the polymer stronger. But if it is lightly cross linked, which means there are a few cross linkages, then the polymer can still be considered thermoplastic, because if we had heat the material, the cross linkages are far and few in between. So, but otherwise, it's the secondary bonds that are holding, making the keeping the polymer solid. So the polymer can become softened uh, in lightly cross-linked polymer. But as the cross degree of cross-linking increases, the thermoplastic effect decreases and it becomes thermoset. Of course, highly cross-linked polymers are very stiff and tough. And we know that these cross linkages cannot be broken by heating the polymer. So that's the third mechanism. So the three mechanisms are longer chain, higher number of branches, and cross linking. So those are the three mechanisms for. Now we saw that polymers are never 100% crystalline, and normally when crystals are formed, there is a small nucleus which forms, and from it basically these spherulates or these chain crystallites emanate in all three directions, or so it uh, grows in a spherical direction. and this will continue until its further growth is obstructed by another spherulite which is growing from another nuclei. But you see that within these we have these amorphous regions, and again we talked about the fact that uh, a single crystallite may contain many chain, and one chain can be part of many different crystallites. Uh, Now, we pointed out that the crystal structure for polymer is formed by chain folding over each other. So that is easier in polymer with small side groups. But in polymers which have large side groups, like these benzene rings, the benzene ring is much bigger than the unit bar itself. So this kind of polymer cannot form crystalline structure, and they are amorphous polymers. So I hope you remember that this is polystyrene. So polystyrene is an amorphous polymer, and just because of the fact that it contains this large, of course, we know that this is representative of the benzene ring. Now, amorphous polymers, as we saw when we discussed glass or ceramic materials, we have amorphous ceramic materials. The behavior is at high temperature, the material flows very easily. As we approach uh, the glass transition temperature, the material becomes very leather-like and rubber-like or leather-like. And once we cross it and go beyond certain point, then it becomes very stiff. So of course, this is a specific volume against temperature. So very liquid-like. The viscosity is increasing as the temperature is decreasing, and it is represented over here. So we see at very low temperature, the material is very stiff and brittle. As we approach near the glass transition temperature, it starts to soften. At glass transition temperature, we have a situation. So they see that it can sustain very large elongations. And of course, at higher temperature, it basically becomes liquid like, and it will continue to flow as long as we apply forces. So this kind of behavior is uh, so it's very similar to the behavior of amorphous ceramics. But in general, we have uh, the the crystalline polymer. We already said that they are never 100% crystalline. So they have amorphous region as well as crystalline region. So if you look at that, so this is the behavior of a glass amorphous material, and this is the behavior of a uh, crystalline material, which is 100% crystalline. But for semi-crystalline polymer, which forms a great number of polymers, thermoplastic polymers are like that, their behavior is shown here. So they have a melting point, but then they have a region whereby the crystals are formed, but the amorphous region is, of course, above the glass transition temperature. So the amorphous region is very ductile, it can be deformed. If we continue to decrease the temperature, there will come a point where that amorphous region goes below the glass transition temperature. So this is a glass transition temperature. In this region, even the crystalline, semi-crystalline polymers, they will become very hard and stiff. But many of these polymers at room temperature are somewhere here. So the room temperature for many of these polymers is in this region. So that the like for example, polyethylene, polypropylene, at room temperature they are in this region. So they have stiffness due to some region being or in a crystalline state, and other regions are amorphous, so they are ductile. If we continue to decrease the temperature, then those polymer will also become brittle. Uh, so I hope this is a very very important property of polymers. Uh, so if we look at these temperatures, then the two critical temperatures are melting temperatures and glass transition temperature. If the material is above the melting temperature, of course it is liquid like. But and if it is below the glass transition temperature, then it is like a glass, hard, brittle. But if it is at near the glass transition temperature, it is uh, uh, rubbery if it is amorphous, and if it is uh, semi-crystalline, then it is stronger. And of course, above glass transition temperature, but the material is, if it is completely amorphous, it is free flowing, like a liquid. But if it is crystalline, then the behavior I already talked about, it will be a solid which uh, uh, is strong and ductile. Of course, when I say strong, the strength is nothing compared to that of metals. It's compared to other plastics. So let us look at some polymers. We saw that polyethylene, low density and high density polyethylene are very widely used, and their melting temperatures are above 100 Celsius degrees Celsius, and the glass transition temperatures are very very low. So in normal operations, they are always in the intermediate stage in this region. So if we look at polyvinyl chloride, its melting temperature is quite high, and its glass transition temperature is also high. It's 105. So at room temperature, it is below its glass transition temperature, which is why PVC, uh, many PVCs are very stiff and hard to bend. If you try to bend them, they will fracture or break. But for PVC, we in many situations we add some plasticizing material and reduce the glass transition temperature to near the room temperature or even below the room temperature, which is why we saw that there are some like uh, uh, some like fall leather is made out of PVC, so it's like leather like, or vinyl flooring that we use, it is also flexible. Uh, for polypropylene, it's amorphous, so we don't have a melting point, and the glass transition temperature is around 100. So, which is why we say that you should never pour boiling water into a styrofoam made out of polystyrene. Now, for polypropylene, we see the melting point is high, but the glass transition temperature is minus 20. So, at room temperature, it is, of course, strong and ductile. But what if you recollect the applications for polypropylene? Some of the applications are like automobile body parts. So for those in those applications, and if these vehicles are exposed to very low temperature, the body panel can potentially fail. So we have to they have to be very careful. If it's being used in such an environment, then the glass transition temperature has to be. Uh, Kyle is saying cold car accident panel. Yes, yes. Some of the panels can fail at low temperature because of this effect. Uh, in Toronto, of course, we don't frequently encounter this temperature, but if we go north or if we go west, the temperature routinely gets very low, and this is an issue. One thing I would like to point out is this is Teflon. So we see that the melting point of Teflon is 327. And incidentally, I was talking about uh, we use Ziploc bags for storing food, but you see the melting point of polyethylene is a little over 100 Celsius. So we should never put boiling hot food into a Ziploc bag or heat the food in while it is in Ziploc bag in a microwave, because we can approach near these temperatures and some of the polymer can leach into your food. So the microwave safe utensils are usually made of polypropylene, which has a melting temperature of 175 degrees Celsius. And of course, kitchenware, again, you see that these are the boiling point of or the melting point of Teflon is 327, which, if you are putting a pan on flame, is not that high. So, which is why it is always recommended to, when you are using non-stick utensils, you should not use it at very high temperature. You should try to cook at medium to low temperature, not increase the temperature to a very high degree. Okay, so any question on this before I move forward?
One question there. So polycarb that means polycarbonate doesn't have. I see there isn't a melting temperature associated. So it just doesn't have a melting temperature. Like I presumably you can melt polycarbonate, but I'm guessing maybe not.
Oh, oh, you mean this? Yeah, so this is also, as I said, you can cause them to attain a molten state by heating them very high. Like polystyrene, its glass transition temperature is 100. But as we saw earlier, like in this case, so if we go above the glass transition temperature, it becomes liquid like. But there is no sharp cutoff point. So as we heat the temperature, it becomes more and more liquid like. So for
I see. So
polycarb,
it's more so it doesn't have a defined point where you can sort of see when that changes.
yeah, exactly. Same
Okay.
with polystyrene. So it doesn't have a
Okay, that's fair. I was
incident.
taking it as not having a melting temperature at all, and I thought that doesn't seem quite right. But now I understand better. Thank you.
Okay. So, and incidentally, polycarbonate is an expensive polymer and it's a very strong polymer. And uh, I think, I'm not sure, but I think it's used in bulletproof glasses as well.
That's what I was
Uh,
just thinking.
yeah, so this is, and it's called an engineering resin. So it's an expensive piece of. So we were discussing picky. Aniket, you still have any a question?
Yes, I have a question.
Yeah,
Uh,
sure. Go ahead.
yeah, so do you mind explaining again why that non-stick thing you were telling to not heat the non-stick pan, non-stick
Yeah,
things
yeah.
more?
So
Like
this
which
is
material does that fall into? Yeah.
so this is poly. This is this material. C. So all these are fluorine. So this is Teflon, and Teflon, we see that the melting temperature is 327. So was your question about this or for Ziploc?
Yes, about this only, the
Yeah,
non-stick thing you were telling. Yeah.
yeah. So this is a non-stick material, but you see it melts at 327. So if you put those utensils on a high flame, the temperature can easily go above 350 or 400, and in that case, the Teflon will basically uh, liquefy and melt and go into your food. So
Yeah,
you
yeah,
don't
okay.
want that.
Because yeah, I was thinking about since other materials, right? They are anyways below 327, right? So we can't use the other materials either, right? The
None of them can be used for sure. But
exactly. Yeah,
the
yeah.
non-stick are used, and but if you read the instruction, they always say, do not use it at high heat.
Yeah, yeah.
So
It has happened to myself. I've already burnt it once, so I was asking.
yeah, and unfortunately, many people do not pay too much attention to it, and it is quite a harmful product. So if we heat it above, so of course, if you have a lot of liquid in the utensil, then the temperature of that area will never exceed this value. But if you are frying something and the flame is hot, of course, where the oil is there, the temperature may not exceed this. But any region which is devoid of oil, that region can go at to higher temperature. And we should definitely avoid using high temperature in non-stick cookware. So any other question? Okay, yeah. So I was saying that we saw that the behavior of polymer is sort of peculiar. Uh, it has some solid-like properties as well as liquid-like properties. So if we look at how solids behave or what is the response of solid to loading is shown over here. So if we have a solid material and we apply a load, it will stretch under the load and follow the Hooke's law. So, and we can represent it by a spring. We know that on a spring, if we put a load, it will stretch, and when we remove the load, it will go back to its original state. So this is the loading pattern, and the response is shown over here. So as long as the load is there, it will be stretched, and once the load is removed, it will go back. Now for liquid uh, or a Newtonian liquid, we know that let us say if liquid is present in a dashpot and we apply a load either upward or downward, this will move. As long as we are applying the load, it will continue to move. Once we stop the application of force, it will stop at that point and will not move further. So the response of liquids is shown over here. As long as a load is there, it will continue to move. And once you remove the load, it will be static at the new position. So if we combine these two behaviors, so we can represent uh, many plastics by a combination of these two behaviors. So this is the loading pattern. Uh, we saw that the elastic material response is like this. A liquid or a viscous material's response is like this. For plastics, which are viscoelastic, they have both these properties. So as soon as we apply a load, there will be an elastic deformation, and then the material will flow under as long as the load is there. And once we remove the load, the elastic component will be recovered, and of course this movement, uh, this component is not representative of that, so what will happen is not very well defined over here. Uh, so this is the typical response of many viscoelastic polymers, not all, but many. Uh, and in fact, plastics have, there are many different behavior responses. Let's look at some of them. I have posted this video and I hope you will see it. So this is a normally called dye swell or Barrett's effect. So you see, there's as soon as the material comes out, it swells up. So what is happening is you can clearly see that it has swelled up. So what is happening is while the material is flowing in the channel, the polymer chains normally they are randomly oriented as we discussed in the first lecture. During the flow, the chains they tend to get aligned to each other in the direction of the flow. They tend to get. a line in the direction of the flow. But once they come out of the wall, the forces that, because this alignment was due to shear forces generated along the wall of the channel. Once the channel is removed, the chains will again tend to get randomly aligned, and that's why they swell up. So this is, let me remove this. So, oops, sorry. So this is a typical behavior for viscoelastic polymers. And this is also called dye swell, Barrett's effect, and there are several names. So extrudate swell, dye swell, or Merrington effect, and Barrett's effect. All these are names for this behavior. So it's and we call these materials non-Newtonian because they do not follow the. And this is a water which is in which color is added. So you can see there is virtually no change, no change in the cross section. Then we have this effect which is called Weisenberg effect. This is a rod attached to a handle is dipped into a liquid which is, so you see this is being rotated. Now you see how is it different? If what would happen if it were water? Does anyone know what would happen if it's water? Would it behave like this? It will not, but rather, and you must have seen that very commonly. If you do something like this, or even rotate water in a ball with your fingers, it will form a vortex which is downwards. So it will be the vortex will be downwards, not upwards like this. Sorry. So some have these videos are posted, so you can see if you want, you can see it on. So this shows relatively a smaller amount of rod climbing, but this one you see is the rod climbing ability is very high. So and these are the three different materials that we used. Again, these videos are posted, and I'm hoping that many of you have seen it. So this is the final video. So you can watch it as it is posted. But the main thing is the material becomes hard. And yes. So you can see if you punch it, it does not splash. And in fact, people can. So you can see she can walk over this pool of water. So that is a shear thickening effect. Uh, these are basically large molecules, and they sort of trap the liquid in between them. And so if you want to move it very fast, they basically form cavities and stop the liquid from flowing. And whereas if you do move your hand gently in it, it offers virtually very little resistance. So those are were flow properties. Then polymers affect both creep and relaxation. What are these? If we apply a constant stress on a polymer, So we see as soon as we apply a stress, there will be a deformation. So there is a strain which is instantaneous. But as long as we are keeping applying the stress, it will continue to deform or slowly over time. And at long enough time, after long enough time, it may fracture or break. Similarly, if we apply a constant strain, if we apply stretch a polymer and then hold it there, of course, as soon as we stretch it, it will develop internal stress. But if we keep on holding it at that strained position, the internal stress will basically decrease. And both these effects are due to the chain-like structure of chain-like molecules that the plastic consists of. Excuse me. So ultimately, uh, with continued stress or with continued strain, the chains they slide past each other and uh, causes additional strain in this case, or cause the stress to be reduced in this case. And now, of course, we know that creep, nearly all materials exhibit creep, but for them, creep is exhibited at a very high temperature. And that creep is due to at higher temperature, the atomic activity increases, and more uh, what we call vacancies are generated, and they facilitate the movement of atoms, or they facilitate diffusion, which causes these. So but the mechanisms are sort of different in polymers as against in ceramics or metals. Now we saw that the crystalline polymers, they always. Any question on the so whatever we have discussed so far? Okay, so we have seen that the crystalline polymers are never 100% crystalline, but they always have amorphous region. So if we look at a small region within the material, we see know that there are amorphous and crystalline region, and we have if we apply load. So what will happen? And initially, in response to this load, the change in the amorphous region will start to stretch in the direction in which the load is applied. And of course, the greater the load, the greater will be this stretch. And if we keep on increasing the load, we see that at this point, that although the crystalline structure is still retained, but those crystals are getting aligned in the direction of the stresses. Ultimately, of course, the crystal structure starts to break, and these chains, some of the crystal will open up, and in this case, we see that most of uh, the amorphous chains are now completely aligned, or mostly aligned in the direction of stresses, so they cannot further stretch. And of course, somewhere here, a neck will be formed, and this neck will continue to grow. And if you recollect the plastic tensile test that we saw, and I think it's also posted on the canvas, you can look at it again. So what happens in this region is when these chains are aligned, this region of the neck becomes strong, but the region above the and below the neck is still weak, so it still has this kind of a structure. So additional load causes, so this the central neck remains as it is, but the additional material above and below the neck starts to acquire this kind of shape. So that structure, the neck continues to grow by drawing in material from above and below the neck. And that's why these materials can deform many times their strain can be 400, 500, or 600%. Uh, and it is due to the fact that the neck continues to grow. Whereas in polymers or in metals, when the neck is formed, the deformation is limited to the neck. Nowhere else the deformation can take place. But in plastics, the deformation continues in region because the neck becomes very strong and the deformation continues in the adjoining region of the neck. So this is what happens. So when we apply stresses, initially there's an elastic region because over here the material can go back to the original space. But once uh, this occurs, then it is an irreversible deformation. So depending upon what kind of polymer we have three distinct behaviors. The first is brittle polymer, which is amorphous, and then we have the semi-crystalline polymer, which are normal plastic or thermoplastics that we have, and then elastomers, which are rubber-like polymers. So let's look at these behaviors. So for brittle polymers, when we apply load, what happens is we see that these bonds they get slightly stretched, but because it is network, this stretching is very confined, not too much, and the material will fail. But for semi-crystalline, we see that as we continue to the amorphous region is stretching until we reach this point where now even the crystals, so this is at the point of approximately maximum load where now the crystal direction is changing in the direction of stresses. And then we have the formation of neck. And as I said, from here to here, the neck will continue to grow. So the stress level will remain the same, but additional material is pulled into the neck. So at this region, most of the load chains are now uh, held together by primary bonds, and ultimately they will start to fail and you have a fracture. Finally, for elastomer, they are lightly linked, cross-linked polymers. So what happens is as we stretch them, the material, the chains, of course, you see that there are cross linkages which are far and few in between. So they will continue to stretch until all the chains are aligned. And if you apply additional load, we go beyond this point, it will fail. If we reduce the load at this point, before this point is reached, it will go back to its original shape. So it's a rubber-like very much. And we call these elastomeric materials. So elastomers. Now we saw the effect of when chains are straightened in one direction, we say that the chains are now oriented because normally the chains are randomly oriented as shown here. But if we stretch them in this direction, then these chains are not aligned in one direction and they will not stretch. So they are very strong in this direction. So if the chains are oriented or if the polymer is oriented, it is very strong in the direction of orientation. So Kevlar is strong due to oriented molecular chains. Similarly, you know the fishing rod, which is made out of fishing not rod, fishing line, which is made out of nylon or ropes. They are very strong compared to the bulk polymer, and they are. It's so because of they have been stretched and the chains are aligned so that the load is taken up by the primary polymer bonds of the polymer, not by the amorphous regions. Similarly, we can have polymer which is or orientation in two dimensions, such as plastic film. The shopping bag that you purchase, you see that they can carry a lot of weight. But if you puncture it and tear it, it's very easy to tear. But if you try to uh, rip it apart by stretching it, these are very strong materials. So they are that's due to alignment. And you have seen cotton tapes. The cotton tapes, they are so strong. If you try, you cannot break them by pulling them apart. But if you tear them, they are very very easy to tear. So they are very strong in the direction of alignment, but very weak in this direction. So that's and orientation is a very very important aspect. So processes are designed to orient plastic to or polymers to gain this strength. So when we align the polymers, basically it is somewhat analogous to cold working, but of course that's where the analogy stops because in terms of increase in strength. But otherwise, the mechanisms are entirely different. Mm, But the analogy can further continue because if we have polymer which has been stretched or oriented, we can so this basically results in increased modulus of elasticity and increased tensile strength. And of course, because the strength is high, the ductility is low. Uh, and similar to cold work material, if we heat treat cold work material, we can regain some of the original properties. Similarly, for these oriented polymers, if we anneal them after orienting them, we can recover some of those previous material. So, from that perspective, it is very similar to cold working in metals. But of course, the mechanisms are entirely different. We already saw stress relaxation, and in fact, uh, so stress relaxation, if we apply a strain and hold it steady, the internal stress basically decreases. And we can define a modulus which is called relaxation modulus, which is the how much the stress reduces over time. And this property can be used to, if we have this property, we can determine the polymer's behavior by drawing this curve. So this curve shows the relaxation changes in the relaxation modulus with temperature. So if at low temperature, we see that the modulus of elasticity is very, very low. So this value is very high and it's almost like horizontal. So it will not change with temperature in a certain region. So it will behave like a solid. But as we approach glass transition temperature, we see that this modulus starts to decrease. And if the material is uh, completely amorphous, it will continue like this. If it is slightly crossing, then we may have a region where it shows some stability. But of course, at high temperatures, it becomes again very much liquid-like. So this will indicate, okay, if you want to process it, we have to heat the material in this region and then we can easily change its shape. And then when we cool it, we can get a solid material. So this property we see, as I mentioned, if it's semi-crystalline material, it has a slope like this. If it is polystyrene, then this thing will continue to decrease like this. This will not be present. And uh, the glass transition temperature of various polymers is shown. So this temperature for polyethylene will be very low. For PVC, it's somewhere here. In fact, somewhere here, I should say. and of course for polycarbonate and others it's higher. Now, one of the most important usages of polymers is in terms of packing materials. And for packing material, we like particularly if you are talking about uh, perishable items like food items or other items in which controlling the humidity or preventing the oxidation is important, then the barrier properties become important. So this table or chart shows the properties of different polymers. So this is over here is permeability, how easily water can pass through a layer of uh, uh, polymer, and this is oxygen permeability. So we see PVDC is this is a very commonly used material in your kitchen. So does anybody know the name? Commercial name? It is the saran wrap that you use. So it has very good barrier property against both against oxygen and against uh, water molecules. The polyolefins, which is basically polyethylene and polypropylene together, are called polyolefins. We see that they have uh, relatively better water permeability properties, but for oxygen, oxygen can easily pass through these membranes. Polystyrene, both water and oxygen permeabilities are high. But then there are other materials where oxygen permeability is very low, even lower than PVDC in some cases for EVOH. And all these, so this is nylon, this is PVC, and so on. Now you see PET, and PET is a plastic from which uh, like the soda bottles or a number of soft drink bottles are made with PET. So it has uh, uh, both oxygen, uh, a reasonable permeability of oxygen, but for water it's not that. The permeability is higher. So this is, let me get rid of this so that sorry about that. I should not have used so much ink. Now, a big, as I keep on mentioning, a big advantage of thermoplastic polymers is ease of manufacturability. So, which is if you can manufacture it very easily, the cost of manufacture is very low, and overall cost is very low. So, which is why now, in terms of ease of manufacturability, you see that the common toothpaste that you use, it has so many layers of plastic. Why? This is the main layer which prevents permeation of oxygen through, so it prevents oxidation of the material inside the tube. But this is of course expensive and not that strong, so it has to be held together by a stronger polymer. So this is low density polyethylene is the casing material which it goes. But low density polyethylene cannot adhere to, the surfaces are incompatible. So it will basically not stick to this. And if we make it, the layers will separate. So in between we have these layers which are uh, compatible to both these material. So they are. So it's a tube basically essentially in which the outer layer is polyethylene, then we have a tie layer, and then the central layer, which is the, this layer. And all of this is processed together. So we have a machine in which, let's say, we have one machine here, another machine over here, and a third machine over here. And all of these feed into one central die, in which there are annular rings, and the material comes out like this. And of course, we fill it with the material and seal it. So all this can be done in one process. So you can see the advantage of using thermoplastic. It's so easy to use and so economical to use. So in polymers, we use uh, almost always have to use some kind of additives in polymers. Uh, and those additives can be categorized into 4 or 5 different categories. The first one is fillers. They can improve the mechanical property, either this or processability and durability or economy. Remember, I said sometimes if we use uh, if strength is not that important, then we can fill the polymer with some cheap material. It will still hold its shape, and you can use very low cost material to fill it. So sometimes like wood flour can be filled with in polymer, or talc can be filled, or calcium chloride, other calcium stearate. So many other calcium carbonate, I should say. So all these low cost materials can be added to reduce cost of the polymer. Then we can have uh, if you want to improve the tensile strength, then we have to add like fibrous material or glass fibers, and the most common material that is used for strengthening is of course glass fiber or carbon fibers. Uh, so all these materials, so these are termed as fillers. Then we have plasticizers. Remember, we talked about when we talked about PVC at room temperature. PVC uh, glass transition temperature is 100 Celsius. So if we want to make it flexible, we can add plasticizer, which will reduce the glass transition temperature to make it flexible rather than brittle. Now, some of these polymers, they can either get oxidized easily, or ultraviolet rays can have effect on them. So we can add some material which will prevent against, if you are using plastic in outdoor environment, the sun rays always contain ultraviolet radiation. So these plastics can get degraded easily. So for outdoor application, we have to use stabilizer which prevent against ultraviolet. Then we have lubricant, as I already talked about. If you want to increase the processing rate, we have to use lubricants, and one common lubricant is sodium stearate. Finally, nearly in all plastics, we all or the vast majority of plastics are inherently transparent or translucent, so they do not have any color. So colors is almost always added to polymers. So color is a very common additive, and of course it has to do with the aesthetics. You want the material to look good, and the colors could be either dyes or pigment. Pigments are solid particles, dyes are liquids. And in many situations, particularly in construction industries, we have to add flame retardants too, because if they catch fire, they will burn at a very fast rate. So we have to add flame retardant, which is chlorine, fluorine, or boron can be added to uh, slow down the burning rate of polymers. So those are the fillers, and of course we already talked about thermoplastics. If we look at processing of thermoplastics, they can be heated and processed, and they can be cooled down, and of course they can be reused a number of times. And the examples are polyethylene, polypropylene, polystyrene. All these are thermoplastic polymers. Whereas thermosets, when we heat them, they form a network polymer, and then they cannot be deformed further more. So they can degrade when heated, but they will not melt. And which is why these are formed inside a mold, and when cured, the mold is opened up and they retain their shape. So examples are polyurethane. So let us look at their processing. One of the important parameters which I discussed earlier, and the shear thinning behavior is very important. So what that is for many, like for polyethylene, polypropylene, they exhibit shear thinning behavior. What that means is, uh, if we are moving, causing the material to move inside a machine, if you want to process it, you use processing machine and the material flows in it. Now, the faster the flow material flows, so this is it indicates shear rate, so flow rate within the machine. The faster it flows, the lower its viscosity becomes. So this is shear thinning. If it is flowing faster, the viscosity decreases and the force required to maintain the flow decreases. So from that perspective, these polymers are inherently suitable for fast production rates. And the shear thinning is usually a power law, and this is the general shape of this power law. So we see that the stresses that are developed are proportional to the shear rate. So the higher the shear rate, the lower is this uh, stresses. Why? Because this power is a fraction, 0.2, 0.1 or something like that. So the higher the flow rate, the lower this material becomes. So let's look at some processing. The most common processing equipment is for thermoplastic polymers is an extrusion. So extruder is just simply a screw which is rotating inside a drum, and due to rotation, the plastic is pushed in this direction, and over here the material has small pellets, and these pellets, they basically, when they are moved, the mechanical energy causes rubbing between additional pellets, and that generates heat. Of course, at the start of the process, when we are using it, the material basically flows out, and when we shut the process down, it's still filled with plastic, and when it cools down, it solidifies. So at the startup, we have these band heaters which heat the material to above its melting point, and then when we start the machine, the material starts to move forward and new material comes in which is solid. And so the major heat that's required to melt this solid comes from the mechanical energy. Of course, it can be supplemented by these heaters, as well as sometimes, in fact, uh, the extruder also has coolers, so it has water nozzles. If the temperature is starting to become too high, we have to spray nozzle water through the nozzles to decrease the temperature. So in general, for processing, we try to maintain temperature within a certain small window. We don't want the temperature to go above it or below it. And because if it goes much higher than that temperature, the polymer chains will start to break. And if it's lower than that, then the viscosity will become too high and the material will not flow. So we have to balance these two things. So heat and friction both are used to melt the polymer and move it forward. But one thing is, you can see that this is a continuous process. So we can extrude profiles which are, and in fact, nearly all thermoplastic have to pass through this extrusion at one point or another. More Most commonly for, if we not for anything else than for mixing color in the plastic, and that process is called compounding. So majority of the plastic that we use is first compounded with colors or other fillers and then processed in a secondary process. And so extrusion is widely used to generate these profiles or shape sheets, pipes, channels, and things like that. And as you can imagine, this is a very, very efficient and fast process, because the faster we process it, the lower is the mechanical energy that is required per unit mass. The specific energy that's required to process decreases, and we can form a very large. Kyle is saying 3D printing. Yeah, 3D printing filament also, because they are polymeric materials, and but normally uh, the extrusion rate in 3D uh, fillers or printing is not that fast as in this, but it's a very similar process. The only difference is they do not have this screw, but rather the filament is pushed into a hot chamber, and it is the force of the filament that is being, because remember over here we have these plastic pellets, but in 3D printing we have a solid filament which is pushed by a mechanism continuously, and that the filament itself acts as a piston and pushes the material out of through the nozzle. Yeah, of course, the filament is. Sorry, I thought you were because that is also an kind of extrusion process, but it's a different process. But yeah, filaments and tubes and all these are made using with extrusion. And in fact, in my lab, I'm working on polymer and composites, and I have three different extruder, large extruder and very small extruder to make filament for 3D printers. And because we are working with on 3D printing as well, so we can develop our own material and use it in printers. So, uh, in fact, I if any of you are interested, you can contact me. I am looking for help in my lab. So anybody who's interested in composite or processing or characterization or so I can use some help. I can hire some of you. Uh, so send me an email if you are interested, and we can discuss this. So this is extrusion processing. So continuous profiles, uh, and then like injection molding or molding is another very commonly used process. Let's now watch this video. It's a small video. Can you hear the sound?
No, sir.
Okay, I guess I will have to disconnect my.
Say we can't hear it.
I also wonder whether or not it is the on YouTube itself, whether or not it's the volume setting for the YouTube. Oh, no, that's full. Okay, it's not that one. No, sir. Your mic is muted on Google Meet.
Okay, maybe that was the issue. Let me try again.
I can hear you now.
Can you hear me now?
Yes, sir.
Okay. So that was the issue. I think my mic, when I disconnected my headphone, the mic was muted. And I was, let me try it once more. Volume is too loud. Let me make it reasonable. Okay.
Apple juice or peanut butter. Whether you're buying apple juice or peanut butter, you've probably noticed that fewer products come in glass containers these days. Plastic pack.
Can you hear now?
Sir.
Okay.
Packaging is becoming more common. Plastic bottles and jars are lighter to carry and leave no shards of glass to clean up if you drop your grocery bag. Many transparent bottles and jars are made from a type of plastic called polyethylene terephthalate, or PET. An automated mixer combines PET pellets with flakes of recycled PET. Reprocessed plastic loses some of its physical properties, so the recycled content can exceed 10%. The PET drops from the mixer into a plastic injection machine that heats it to a piping 600 degrees Fahrenheit. The dry raw material melts into thick and gooey liquid plastic. The machine then shoots it at high pressure into a mold. This plastic injection molding process casts pieces of plastic called preforms, starter shapes that subsequent machines will transform into bottles or jars. The molded preforms harden almost instantly, thanks to a built-in cooling system. These preforms are now on their way to becoming single-serving juice bottles. This is another plastic injection molding machine. It uses the same method to make preforms for a different model, 1.5 to 2 liter bottles. The preform's next stop is a machine called a reheat stretch blow molder. In a matter of seconds, it heats each preform just enough to make the plastic malleable, then inserts a rod to stretch the preform lengthwise, while at the same time blowing in air at extremely high pressure. This forces the preform into a bottle-shaped mold. Cold water circulates within the mold to cool and set the plastic almost instantly. This lightning-fast machine churns out 10,600 bottles per hour. No wonder we've had to show it to you in slow motion. A conveyor belt transports the finished bottles to the packaging area. Before blow molding, the preforms for certain models first pass through an oven. A A technician sets the heat level of each infrared oven lamp individually, applying more or less heat at various points to influence the thickness and shaping of the plastic. From the oven, the preforms go into another reheat stretch blow molder that transforms them into peanut jars. It's the same process for this peanut butter jar. After molding, the machine instantly cools the plastic, locking in the shape. The factory pulls samples off the line at regular intervals for quality control testing. Technicians measure the thickness of the plastic and perform a compression test to gauge its strength. They verify the sample's dimensions and capacity. They also evaluate resistance to vacuum pressure, because containers are often vacuum sealed after filling. Some models must also be strong enough to resist the pressure of their contents, carbonated soft drinks for instance. The recycled material used in making these bottles and jars doesn't come from used plastic containers. For hygienic reasons, the factory recycles only new plastic left over from its manufacturing process. The finished containers, of course, are fully recyclable. They're typically reprocessed into other plastic products or into products that contain some plastic.
So you see that the processing is extremely fast. When I said that faster you process it, the more economical it becomes. And you saw the speed at which it was processed. So injection molding, by the way, can you hear me?
Yes, sir.
Thank you. So injection molding is a very the most widely used plastic processing equipment, and so all the small plastic parts that you see, like the caps and even a small, maybe something like this, all these are basically made with injection molding. And so injection molding, again, the process is similar. You have this. In fact, I think the next one is that. So this is an animation. You can see you put the pellets in, and it collects. The plastic is collected in a chamber, and then it's pushed at a very fast pace inside the mold. You can see the process. This is we collect some plastic in the chamber and then push everything in a very fast pace. So this is, and in fact, there are small handheld machines in which basically there's a small chamber. You can put molten plastic, and then there's a worm and gear arrangement. Once the plastic is molten, you can push a piston rod down, and the plastic forms disposed into a mold. So this is injection molding, and incidentally, these injection molding machine, of course, you saw the fast processing of those bottles, but the injection molding machines are also very fast, and these can be very huge also. And because you see, when you are injecting material, the mold is connected here. So due to high pressure, there is if we do not clamp it very strongly, the mold will open up and the material will lost. A lot of material will be lost here. So these machines, first of all, this mold has to withstand very high pressures, and it's operating at a very high speed. So these molds also are very expensive. So for large machines, the molds can be in hundreds of thousands of dollars. So they are only economically possible when the production rate is very high. So in high, these kinds of machines are used to produce very high volume products. So you see this mold, some small molds, they do not require cooling, but when we have larger molds and we want faster processing time, then of course we have to, as soon as the material is injected, these are cooling channels when the water cools it down and the mold opens after the temperature drops a certain degree so that the material is solidified and can be ejected out of the mold. So this is injection molding. I forgot what this. Let me see. Let me first of all go over. So the summary is thermoplastic. We discussed different thermoplastic, elastomer, the thermoset material, and their processing. And so I will. Oops. Let me start this video, and if anyone wants, they can. Oh, is it the same one? Why is it the same one? Okay, I guess that was the last of it. Maybe.
Plastic fluid is then forced through a die opening where it is shaped and cooled into solid form. These forms include bar and rod, tube and pipe, or profiles such as angles and other cross sections. Flat products such as sheet and plate, flexible film for bags and packaging, monofilaments, and wiring insulation. Thermoplastic feedstock is fed to the feed barrel from the hopper. Hoppers are typically vacuum fed automatically, but may be filled manually. As the feedstock enters the feed barrel, it is driven forward by the rotation of the screw. The feedstock plasticizes or melts as the rotating screw drags it forward. This is referred to as drag flow. Drag flow causes the thermoplastic molecules to slide over each other, creating frictional heat, which melts the material. External heating bands provide additional heat to the feed barrel, bringing the material to its final temperature. Two of the principal plastic extrusion processes are profile extrusion and blown film extrusion. Profile extrusion is a horizontal process used to make long, continuous shapes having a constant cross-section or profile. The profile is extruded into a long, horizontal cooling tank or trough filled with water. This water cools and solidifies the extruded plastic as it exits the die. At the end of the cooling tank, pull-off holes pull the profile away from the die at a uniform, controlled speed. As the profile is pulled through the haul-off rolls, a cutter shears it to the required length for further processing. Some profiles are difficult to extrude because of shrinkage and the flow characteristics of the plastic. Typically, generous internal and/or external corner radii are used to minimize these concerns. Additionally, some profile extrusions may also require inline sizing to achieve dimensional tolerances. The blown film extrusion process uses an extruder to pump molten plastic vertically up through a die, having a 360-degree annual opening on its top. This produces a tubular film extrusion, which is subsequently filled with air. As a result, the tube expands out into a bubble, having a diameter larger than the diameter of the annular opening of the die. The tubular bubble cools as it is pulled up. When sufficiently cooled, the bubble is flattened within a collapsing frame. The flattened plastic is then pulled through a series of rolls, commonly referred to as nip rolls. Nip rolls help to maintain tension on the flattened plastic film as it is guided to a winder and wound onto a core for later use.
Okay, thank you. Any questions? I know that we are past 5 o'clock. Uh, so this is time for the office hours. So I'm open to any questions.